Welcome, everyone. I appreciate the opportunity to talk to you all today. I know you're all busy, so I hopefully you'll get something out of this presentation. I'm just going to talk really at a high level about chemical cleaning, but the thing I guess I want to emphasize with everybody is the success of chemical cleaning is all about the details, and it's all the little details that make for a successful chemical cleaning, and cutting corners on those details leaves you at risk for not having a successful chemical cleaning. If you're going to chemical clean your Hrsg, you absolutely need to get somebody with some technical knowledge involved, both on your end and also on the chemical cleaning supplier you're going to use. And I can't emphasize that enough. So Barry started talking about reasons to chemical clean. So really there's kind of like three reasons to chemical clean. Are you going to do a pre-operational clean? Are you going to do a chemical clean because your deposit weights fall into that criteria that Barry just set? Or has your corrosion got away from you and you have under deposit tube failures that you have to address? So for a pre-operational clean, this is, you just built your Hrsg and you're going to say, should I chemical clean it? Well, the reason why you want to do a pre-operational chemical clean is you want to remove any mill scale, any cutting oils that may be present. If the tubes were sitting somewhere for a while, were there any preservation agents applied to them prior to the install? And fundamentally, to remove any corrosion cells that are present and to passivate the surface prior to the initial startup of the unit. Here's an example of one of the units from my previous work. You can see at the left, we purchased a stranded asset that was not very well taken care of. It had never been put in operation. It was put up for sale. We went ahead and bought it. And, as you can see with some borescopes, you can see it wasn't really protected while it was sitting there. You can see the start of corrosion cells, etc. And then the picture to the right is the pre-operational chemical clean, and that's what it looks like if you do a pre-operational clean. I know there's people out there that want to cut corners when it comes to doing pre-operational chemical cleans, but just strongly suggest that you don't do that. It's an opportunity to, like I say, stop any corrosion cells that may have started during installation, and it gives you the opportunity to put that protective passive layer down, and it gets you to start with a unit that's fundamentally clean. And then, as Barry said, if you fall into that category after you've taken a tube sample that you've got high deposit weights, then and those deposits typically are going to be in your evaporator, HP evaporator. So you're going to go in and clean those to remove the iron. I can't emphasize enough. This is the little details that tend to get forgotten or corners get cut. You really, if you're going to take the tube sample and you're going to get a deposit analysis, you need to find out what the constituents are there, because, is it just iron? Does it have copper in it, which is typically not too common because Hrsgs usually don't have any copper in the condensate and feed water. Have you had lots of condenser leaks where you might have a bunch of silica or calcium in the deposit? Those things are important to know, so to help you determine the solvent selection. And then once you have those tubes out, you can do dynamic or static tests to ensure that the chemical cleaning solution that you're going to use will actually remove the deposits that you're going after. This is the one that you don't want to see. As Barry has described, this is still one of the top tube failures from a water chemist perspective and Hrsgs and the high pressure evaporators, and that's hydrogen damage. These deposits are very, very difficult to remove, and they take some extra care to try to get them removed. Fundamentally, if you can get a sample and find an under deposit corrosion cell like you see in this picture, then what you really should do with it is give it to a chemical cleaning contractor and have him run some solvent tests both static and dynamic, to figure out how long you need to chemical clean your unit to try to remove these cells. And I can tell you that at a minimum, if you know you've got hydrogen damage, but you don't have, you know, a tube sample of these corrosion cells, you should plan on at least a minimum of 24 hours contact with the solvent that you're going to clean with. The reason why you want to run dynamic and static tests, though, you can find out that these can take, 76, 90, 100 hours to remove. And fundamentally, if you're going in to chemical clean something like this, you need to know what the criteria should be for how long you need to have that chemical in contact with the corrosion cell to remove it. And the downside with these is these will be in very local areas. And one of the things you use to determine when a chemical clean is done is the supplier will be running concentrations of the solvent in the circulation path, and he will be running iron. And what normally happens is when your iron levels out, which indicates you're not picking up any more iron, and your chemicals aren't dropping anymore, which indicates they have no more iron to remove, you typically will say your chemical clean is done. When you're trying to remove these type of very localized deposits, you can see your iron and your iron level off and your chemical cleaning concentration level off, and think that you're done cleaning, but you're actually not, because these cells are still out there being removed. But the amount of iron you're going to add from these very localized areas won't have much impact on the analysis that's being done. So that's why it's really important to understand, by running static and dynamic tests on your samples, how long you really need to clean to try to remove this kind of stuff. So I'm just going to go at a very high level, going to talk about chemical cleaning and the basics. I always chuckle a lot because I say, we talk about chemical cleaning being very complicated and et cetera. But if you just take a step back and think about chemical cleaning, all you're fundamentally doing is taking a solution, pumping it around in a circle, heating it up, and letting it go around in a circle for a while, and then draining it to some type of tank. So when you think about that, it doesn't sound very complicated, but obviously, as I started with the presentation, the devils are all in the details to having a successful chemical clean. Basically, the 4 criteria you need is obviously need to have a solvent that's going to remove the deposit. You need to have some temperature. You need to have proper flow. In other words, you need to get the flow to the areas that you need to clean, and you got the time. And as long as you have all of these, you'll have a successful chemical clean. There's all kinds of solvents that are most likely used. You have organic solvents. You have things like EDTA, citric acid. Although just a subtle reminder, there are utilities, and the one I work for is one of them that won't allow the use of citric acid. If you go start looking around, there are people that have had some bad stories about using citric acid. It's not a very strong acid, and probably for a pre-operational clean, it would be acceptable, but I would really suggest that you don't consider something like that if you're going after heavy deposits. On the inorganic side, there's hydrochloric acid, and there's hydrofluoric if you're trying to remove silica. What's the difference between the two? Well, organic solvents tend to be less aggressive. You definitely don't have to worry about stress corrosion cracking when you're using austenitic stainless steels if you're using organic solvent. They're also less aggressive to the base metal. You do need to circulate them, and they're safer to handle than mineral acids. But I say that, but the caveat is your safety precautions, whether you're using organic or a mineral acid, are still going to be the same. You're going to be wearing goggles and all that kind of stuff. So even though they're not quite as, I guess they're a little more safe than mineral acids, fundamentally the safety aspects are going to be treated the same. And in the case of organic solvents, they typically complex the iron. That's the method they use to remove the iron that's deposited. Mineral acids, very aggressive. They're generally cheaper. They work at lower temperatures. You don't necessarily have to circulate them, and they actually dissolve the deposits. So Barry talked a little bit about this. So the chemical cleaning, the basic solvent selection, you really need to do a deposit analysis. And then you can, once you do that, find out what it's at, you can do some static tests and or a dynamic test to see how well the solvent's going to work and how long it's going to take to remove it. A warning is typically this testing isn't performed if iron is the only constituent in the deposit. What you see a lot of times is people won't do this because they're going to assume it's all iron. When you make that assumption, you increase your risk of not having a chemical clean. And when you think about the amount of effort, time, and cost to do a chemical clean, is it really worth taking a chance by not doing the analysis to figure out what the deposit is? The majority of the time, it's going to be iron, but there are going to be those times that it's not. And then just a small warning, this is just kind of an arbitrary number based on my experience. If you have deposit weights that are greater than 50 grams per square foot, or you're trying to go after under deposit corrosion cells, or you've operated with numerous condenser leaks, you really should be doing static and dynamic tests to ensure that the solvent you're using and the time that's necessary to remove those deposits, you have a good handle on them before you do your clean. And I can't emphasize this enough, when you're choosing a solvent, fundamentally you have to make sure that it's going to remove the deposit in the time frame that you want to do that. But if you find out that you got a couple choices there that are going to accomplish that same task, then you really need to be looking at the waste disposal end. Sometimes the waste disposal end of a chemical clean can be half the cost depending on what solvent you're using. So you need to try to factor in how you're going to manage the waste and dispose of the waste as you try to make the decision on what solvents you're going to use. But fundamentally, that's only secondary. You still fundamentally have to find a solvent that works first. So waste disposal, you really need to have your environmental subject matter expert needs to be intimately involved in the waste disposal discussions, because regulations continuously change. So whoever your environmental person is, he really needs to be on the front end of the planning of a chemical clean. The methods of waste disposal needs to be planned up front, including any or all necessary approvals or permits that are needed. And I really strongly suggest that your chemical cleaning team, and I would include the potential contractor in this, you should really run some tabletops and ask yourself these type of questions. If I'm doing my chemical clean and I'm in the middle of the chemical clean, have I had problems and I filled up all my frack tanks, what am I going to do? What am I going to do if the waste is deemed hazardous? I wasn't planning on it being hazardous. It turns out that it's hazardous. Major spill that leaves the site. How am I going to manage that? How am I going to manage spills? I'll just tell you a quick story. We had a situation where we were chemical cleaning a supercritical unit, and we had a existing metal cleaning waste tank at the site that we put all the waste to. And then we checked the waste, and it came back hazardous for chrome. So because of that, our waste disposal methods had to change. But in the meantime, and we managed it, it added costs to the chemical clean, et cetera. But we ended up getting in trouble with the local agency because we were not aware that when the chemical cleaning waste became hazardous, we were required to have somebody once a shift go out, walk around the tank, look at the piping and make sure there were no leaks and document that. Well, we had people, as long as we had chemical cleaning waste in our tanks, we always had people going around and inspecting, making sure there were no leaks for the length of time that the waste was in the tank, but we did not document it. We weren't aware we had to document it. So that's why it's important to get your environmental subject matter experts in on the front end of these planning stages, so that you can have these discussions. And like I say, do tabletop exercises to ask these type of questions to make sure you fully understand what your requirements are if these type of things go wrong. And unfortunately, these type of things go wrong during chemical cleans. The other basic thing with solvent selection is you're going to use a corrosion inhibitor. And the way I like to describe a corrosion inhibitor is I say that your chemical cleaning chemical is the dumb chemical. You put it in there and all it does is look for iron, and it just goes after whatever iron it finds. Well, then you put the corrosion inhibitor in there, and what the corrosion inhibitor is, it's the smart chemical. So when the dumb chemical is looking for iron and it sees some iron that's base metal, the corrosion inhibitor hits it in the back of the head and says you can't do that. So the corrosion inhibitor is what's going to protect the salt, protect your base metal from having the chemical cleaning solvent go after it. The contractor will typically recommend the corrosion inhibitor to be used based on the chemical that you're using. Temperature is also important. Generally, for any chemical reaction, right, the higher the temperature, the quicker the reaction goes, the more aggressive the reaction is. But the higher the temperature that you go, the more ineffective that your corrosion inhibitor can be. So there's kind of a balance there. So I just threw up here some different temperature ranges that are kind of typical for the various solvents. Again, these are the type of discussions that you would have with your chemical cleaning contractor as you're laying out your plans to do the clean. Chemical cleaning flow, the basics. You can't clean anything if the solvent doesn't get to it. That's kind of the fundamentals of it. The general rule of thumb is the chemical cleaning contractors will tell you that you should have about 2 feet a second at a minimum of all circuits being cleaned. And you should try not to go above 5 feet a second because of the effectiveness of the corrosion inhibitors. So you should always ask your chemical cleaning vendor, especially if it's a brand new clean that you're doing, it's never been done before. Either you or the vendor should be doing the calculations, and you should ask for them to find out what the flow rates are in the various circuits that you're cleaning. And if the flow rates in a circuit is above the 5 feet a second, then you should be having some discussions with the supplier about these corrosion inhibitors. They can supply you corrosion rates at different velocities for these corrosion inhibitors, which will help you make a decision on what inhibitor you might have to use. And then obviously with flow, you're going to generate hydrogen gas during the chemical clean. Hydrogen gas tends to go to the high spots in the cycle, so you need to make sure you're venting so that you don't become airlocked when you're cleaning. I can't emphasize enough, when you do a chemical clean, don't assume that your valves are going to hold. What I usually suggest is when you're going to do a chemical clean, you pull out your flow diagrams, you highlight the chemical cleaning path in one color, you highlight the isolation valves that you're going to use to keep the chemical from getting to places you don't want in another color, and then you go around that whole flow diagram, and you also, in another color, highlight the dead legs. In other words, let's say you got a pressure transmitter, you're going to isolate the pressure transmitter, but you're still going to have a dead leg between the piping that the pressure transmitter is connected to and the valve. And then based on that, you need to be able to look at all those and determine, how am I going to flush chemicals out of my dead legs? You also need to ask yourself, how am I going to flush chemicals if a certain valve leaks through during the clean? How am I going to flush that? And let me take a step back first. How am I going to know that that valve is leaking through? And then once I know it's leaked through, how do I flush that? If you don't have a good way of knowing it's leaking through or a good way of knowing how to flush it, then you probably need to put a blank in that valve. Don't assume valves are going to hold. And these kind of little details are going to have a big impact on your ability to have a nice startup after your chemical clean. Basically time, as I always say, and people have done chemical cleans know this, as soon as that chemical goes in the in for circulation, somebody's going to come up to you and ask you how long before you're going to send it out to the frack tanks. And I always chuckle on that when you think about the amount of time, effort for planning, the amount of time and effort to set up all the equipment that's necessary, et cetera, et cetera. You do all that, spend all that money, and then you're going to argue about, can I get this clean done in 2 hours versus 4 hours versus 16 hours? It just seems kind of foolish when you take a step back and look from the big picture. You go to all this effort, and the thing they want to do is cut the time that you're circulating. So don't let them do that. The whole reason why you spend all this money in that is to clean the units. So don't cut corners here. So now I just want to share with you some words of wisdom that I've learned over the years. Some things maybe you can take back. Hopefully 1 or 2 of these may be something new to you. But basically, as I said, the chemical cleaning details are pretty easy. You need to pump a solution round and round. You need to heat it up. You need to pump the heated solution round and round, and you need to drain it. But as easy as that sounds, the devils are always in the details. So you need to pump a solution round and round. So things you need to determine: what section of the Hrsg are you going to chemically clean? Typically, it's not a pre-operational clean like Barry mentioned. It's always going to be the HP evaporator circuit. All chemical cleaning piping is going to be temporary, so it needs to be installed. You need to determine the flow path for where the solvent will enter the Hrsg and where it will leave the Hrsg, and this includes all the temporary external piping for contractors' equipment. You need to heat the solution up. If you don't have a source of steam, in other words, another unit on the site that you can get auxiliary steam for, you're going to have to bring in a temporary aux boiler to provide the heat that you're going to need to heat up the solution. When you do that, you need to be talking with your environmental subject matter expert to find out if there's temporary air permits. Are there temporary permits that are needed to have fuel oil on site to heat, to fire the aux boiler, et cetera. You also need to work with your contractor and have discussions with them when he recommends an aux boiler. You need to ask questions like, okay, how long is it going to take to heat up? And you got to decide if that's acceptable. And I also always want to remind people that you're supposed to watch your temperatures, but remember, the temperature that's the most important temperature is the temperature right at the surface where you're trying to remove the iron. And I've seen situations where you've seen return temperatures on a chemical clean be at, let's say we're trying to clean at 200 degrees, be at 200 degrees, but look at thermocouples on evaporator circuits or on the cleaning circuits and see some of them that, are still only 185, 190. And that's really the temperature you're most concerned about. You want that temperature to be the temperature that you're needed to remove the deposit. Covered that. The chemical cleaning contractor is going to supply you all the equipment that you need. So you can see on this picture, you can see all the temporary chemical cleaning piping laying on the ground there. You see the heating station where you're going to heat your chemicals. So there's going to be a steam supply to that. You can see a chemical cleaning mixing station. And then obviously the pumps that are actually going to circulate the solution to the Hrsg. takes up quite a bit of real estate. So that's one of the things you got to figure out. Where are you going to put all this stuff? Where are you going to run this temporary piping? Because usually what makes it interesting, right, is you're usually doing a chemical clean at the end of the outage. So these areas that you see all this equipment set sometimes isn't available for a while because there's other work going on. So it's kind of a nice dance, so to speak, of how the maintenance can get their work done and the outage work done while you can get this chemical cleaning stuff put into the area you need it. This is just a picture of a frac tank farm. You can see this is the middle of winter. You notice the it looks like wood boxes. That was just the chemical cleaning piping going out to the frac tanks. And this plant decided to put it in wood versus going to the effort to insulate it. So here's the lessons learned for all of you that if you're not familiar with frac tanks, they're basically a 20,000 gallon tank that you bring in and you hook up a series. I guess you hook them up in parallel. You bring a bunch of tanks in, and then your chemical cleaning waste goes to these tanks. With these tanks being used in the fracking industry in the north and in the oil refinery or oil fields in the south, you really need to inspect these tanks when they come on site. And when I say inspect them, when your guard at the front gate says there's a frac tank here, you need to send somebody out there and go pop the lid on the frac tank and see if it's clean. If it's not clean, you need to tell the driver to take it back. You do not want the driver to set the tank and let him get off site before you inspect them. Because whatever's in that tank, once they leave, you now are the owner of it. And this is a picture of a tank that we rejected that had some type of organic stuff laying in the bottom of it. So just a word of a wise, you need to be they should look, fundamentally, they typically will steam clean them and they'll be dry. They'll look perfect on the inside. There won't be any solution or no moisture seen in the tanks or anything when they arrive on site. If you're seeing stuff like this, I would just tell them to take it back. So the chemical cleaning process itself, so you've got your tube sample, you found out you got to clean it, you've done your analysis, you find out the solvent you're going to use, you get all your chemical cleaning piping set up, et cetera, et cetera. Then you just go through the process, right? You want to hydro your unit. Once you hydro it, you're going to backfill your superheat with ammoniated condensate. You're going to start circulation and heat it. You're going to inject chemicals and circulate it. Then you're going to flush and rinse it. Passivate the surface with another step, and then you're going to go ahead and have fundamentally the waste disposal to take care of. So let's talk about the hydro. I can't emphasize enough how important a hydro is to do. Anytime you have a leak, it is manageable and fixable when it's only water. Once you put chemicals into the circuit, any leaks that you have become more difficult to manage. And when you hydro the chemical cleaning piping, the temporary piping, I've seen situations where somebody's seen just a little drip and said, that's good enough. Leaks do not get better as the clean goes on. When you put solvent into the circuit, those leaks will get worse. So my message to you is do a good hydro and don't let anybody try to convince you that that small drip isn't worth going to the effort to fix. You want to go into a chemical clean with a tight system, because even with a tight system, things are going to start leaking after the solvent gets put in. I guess we kind of copied this. I said, you want to check your temporary piping for leaks. Like again, I can't emphasize enough, leaks can be fixed and managed when it's just water. Once you get the solvent in, it becomes a lot more dicey. And then obviously your superheater will need to be backfilled with ammoniated condensate. Especially you will have enormous amount of fumes getting back out through your steam turbine if you don't backfill the superheater. And you're also putting the ammonia in there just in case some upset occurs where you get some chemical back into the superheater. You'll have some high pH water in there to neutralize it. Obviously, you need to walk down the system while you're heating it up. Again, trying to manage any leaks that could be that might pop up. And as the piping heats and expands and all that kind of stuff, and you're going to be venting the areas that are high points in your system to get rid of any gas, any air or anything that's in the system. Once your temperature's there, your air's out, no leaks, return temperature's where it needs to be, you're going to go ahead and inject your chemicals. And then once your chemicals are injected, your chemical cleaning contractor will run tests. And this is just a picture of a typical chemical clean using EDTA. You see the blue line is the chemicals. You can see this particular clean, we went in with 2%. And as you can see, as it started picking up iron, the chemical concentration started to drop. We had a habit that when our chemicals leveled off, we would inject another slug of chemicals to see what the iron would do. We've seen situations where the pink line is your iron. You can see it's pretty steady. We've seen situations where we've hit it with another slug of chemistry and we'll see the iron spike up. In this case, you can see we slugged it twice, didn't see the irons go up, and at that point we decided that the clean was done. Can't emphasize enough, if you want to know how well your procedure worked and how well of a job you did flushing and rinsing, it will be reflected on how difficult your startup after the chemical clean will be from a chemistry standpoint. If you haven't rinsed and flushed, you will be chasing chemistry during that startup and have all kinds of holes as you're trying to manage chemistry because you didn't get everything flushed out of the system. Here's an example of an inadequate flushing. You can see the foam there. That's representative of some EDTA that was left behind. So that just like I said, need to pay attention to the flushing. And then the chemical clean passivation layer. Once you clean your unit, you are going to be left with basically a bare metal surface. So at the end of the chemical clean, you go through what's called a passivation step, which forms a small magnetite, a very thin, weak magnetite layer over all the cleaning surfaces. This is not the protective layer that you get when you're running your unit. But this is just a very weak layer. It's so weak that if you go in, you could actually rub it off with your finger. And really the intent of that layer is just to protect the surface from having after rust while you're returning everything normal and getting things ready to start the unit up. I can't emphasize enough, and especially in today's world, if you chemical clean a unit, you need to return that unit to service immediately. Where I used to work, we basically said that the unit had to be ran for a minimum of 76 hours at full drum pressure to make sure that the right protective passive layer is formed. That 76 hours was just a, kind of a guess on our part, but we were getting into the situation where we would chemical clean a unit and then dispatch would decide they didn't want that unit. And if you do that, that passive layer that you form during the chemical clean is not going to hold up and you're going to have quite a bit of after rust. So we said, hey, if you're going to go this effort to chemical clean the unit, you need to put it online and run it for a few days, and then you can do whatever you want with it. So keep that in mind. And I put this slide in here again. It wasn't by mistake. I just put this slide in here to remind you that, man, waste disposal and handling the waste and managing that part of the chemical clean can't emphasize enough how important that is to your success of a chemical clean. You know, running out of frack tanks, you know, again, waste that's deemed hazardous. What if you got a major spill? You know, management of spills. You're going to have all this chemical cleaning temporary equipment there. Are you going to bring in temporary dikes and stuff around that equipment so you can manage the leaks? You have to look around your plant site for where all your storm drains and things are. Do you put rubber covers over your storm drains in case you have a leak so that the chemical cleaning can't get into your storm drain system? I can't emphasize enough that the waste disposal and managing the waste is one of the more difficult parts of a chemical clean, and you really need to make sure that you looked at all the possibilities of things that can go wrong there so that you can be prepared if worst case scenarios happen. And I guess I would be amiss if I didn't talk safety real quick. You'll get SDSs with all the detailed necessary safety precautions for the different chemicals you're going to be used. You'll get those from the supplier. You need to look at those and make sure that you have the correct safety equipment and things necessary to manage those chemicals when they get on your site. You know, temperature, you're going to be cleaning above 140, and anything that's above 140 will need some type of personnel protection. So all that temporary piping that you have out there, you know, you're going to have to think about how you're going to have personnel protection because it's going to be hotter than 140. You know, you're going to have hydrogen gas generated during the clean, so no smoking, welding, cutting, that kind of stuff can't take place. Lots and lots of tripping hazards. If you remember the picture I showed you with all the piping laying all over the place, there's lots of areas to trip and fall. You also need to determine what areas that the safety equipment will need to be worn in and what level of safety equipment is needed. And I highly recommend that you have a safety brief in the control room at the start of each shift with the chemical cleaning contractor and the operators, so you can all kind of discuss where you're at in the chemical clean and what kind of safety issues are going to happen over the next 8 or 16 hours, depending on how long your shifts are. And I believe, Bob, I believe that's it.
All right, thank you very much, Doug. I found that very informative. There are no questions in the chat right now for you specifically. So let me ask, anyone has a question for Doug, push the little raise your hand button or add it to the chat. Barry, there's still a handful of questions from, while we wait on those coming in, a handful of questions for you from the previous presentation. Do you want to read those or you want me to do it?
Where do I see them, Bob? I don't.
Okay, well, I'll do it. They're in the chat. So
and sorry, just before you do that, it looks like
yeah.
there is one from Yafim. When you do pre-cleaning lab evaluation of various cleaners, how do you know that you have a representative tube sample? That's for Doug.
Yeah.
You don't, and that's the unknown in it. You just have to kind of you have to go by the expertise of a guy like Dr. Dooley that says these are the areas you should check. And then you also got to kind of assume that all the tubes see the same water, the same contamination. So you're going to have to make some assumptions that that tube is going to be representative. And then the other things that you can do is you can add additional time to your chemical cleaning. You might want to look at maybe boosting your temperature, maybe 5 degrees or 10 degrees if you can do that, and corrosion rates stay where they are. So we always accepted the fact that there was going to be some unknown in that area, and we always added some extra margin into things. You know, that if the static test said it'll be cleaned in 6 to 8 hours, we would typically put in our procedure that we were going to clean for 12 hours. We would just do some things like that to try to compensate for the fact that you're right, you don't necessarily know if you have the worst sample on the circuit.
Okay. Doug, there's another question for you. Do you recommend hydroing the boiler after the cleaning is complete to determine if a leak was created by the cleaning?
So, yeah, you would, I guess the recommendation would be if it's a pre-operational clean, it's probably not as necessary. But if it's a operational clean, especially if you're going after hydrogen damage, you absolutely should do a hydro after a chemical clean. And what's unfortunate about that, even with a hydro after a chemical clean, if you're going after hydrogen damage, there's probably a good chance within 2 weeks you'll come back off with a leak.
Yeah. How does that final hydro affect the passivation stage?
Yeah, that's that's the other piece of it, right? So really, I don't have a good answer for that, because what you really want to do, if you should do that hydro, and you should go ahead and start the unit up. If you put that water in there and you got a leak and you got to come off, then it's going to be what it is, and there's not a whole lot you can do about that. You should have a pretty good idea how tight your boiler is during the chemical clean also. I mean, evaporator circuits. If the unit's not leaking during the chemical clean, you're probably going to be okay. But the caveat with that always is if you're going after hydrogen damage, that can put some real monkey wrenches in it.
Yeah.
Yep.
Yeah, there's a question that asks, can you elaborate a little more on the static and dynamic tests that you discussed?
Okay, yeah, that's a good question. I apologize for not talking about that earlier. So basically what a static test is, you'll take a piece of what the chemical cleaning supplier will do is he'll take a piece of your tube, just a small section, maybe a 1-inch cross section of your tube, and he will put it on a hot plate with a stir bar with the solvent that you're going to use. And then he's going to basically watch it to see how long it takes for the deposit to drop off the tube. One caveat that I'd like to mention with that is what typically happens when you do that is you will see the deposit break up and fall to the bottom of the beaker. Don't let the contractor tell you that means it's clean. We used to say it ain't clean till there's no stuff laying in the bottom of the beaker. Once you've got that all done, you kind of look at the results of the static test, because the static test, it's it's going to sound dumb. It's not dynamic, so it won't take into account the effects of the flow with removing and dissolving the solvent. So once you do the static test, and let's say the static test said it took 8 hours for it to completely dissolve, then you can take another piece of that same sample, and they have what's called a test loop where they actually pump the solvent around to simulate chemical cleaning it. And what will happen is the dynamic loop, because you have the flow piece of it with the chemical cleaning going on, it will typically show you that if it took 8 hours in a static test, it may only take 6 or 5 hours to get it completely clean in the dynamic test. So I usually use the static test to determine the solvent and the temperature, et cetera, and then I'll take that and model it with the dynamic to make sure that it gets me the results I want.
Okay. It's a question from Franco Silva. It says, if the solvent concentrations are okay and the iron concentrations are okay, then how do I know exactly when the end of the cleaning? Because if you continue, you may damage the material. I think you covered that, but maybe you can comment briefly on it again.
Yeah, so these inhibitors work pretty well. Maybe I emphasized, put a little bit of fear of God in everybody by the way I talked about the inhibitors. They work pretty well. So the message would be, you don't really know, but we always opted on the side of going longer. I always believed, after talking with some of the chemical cleaning suppliers over the years that I was working at American Electric Power, that it's my belief that if an inhibitor was to break down during the clean, that you would see your iron start taking off on you. And talking with the chemical cleaning contractors, they believe that that would be the case also. Now, they've never seen that happen. So while I was extending chemical cleans because I wanted to have more time, I always paid attention to see if I started seeing something like that occur.
Okay, good.
Yeah.
All right. A question from Gene Cotton. Will adding film forming substance to the hydro water after cleaning help reduce rusting?
In theory, it should not, no, because you need, my understanding, for those products to work, they need temperature to activate them. So they're not going to be able to do anything if you're just putting in with the hydro water.
Okay. Neil Hawkins comments that one thing he likes to do is to have the chemical clean run through a slipstream with a pup piece of a tube sample to monitor it during the process. Have you had experience with that?
Yeah, that is, as I said earlier, paying attention to details and doing everything you can to make sure you know what's going on, et cetera. That is outstanding way to know what's going on. There's some cost involved in doing that, but I tip my hat to Neil, because yes, if you can get people to do that for you, absolutely. Nothing better than pulling a sample during the clean and see what's going on.
Yeah, good. Okay. At this moment, that's the question so far for you, Doug. Stand by in case there's more, though. Barry,
right.
we have a few minutes to go back and grab a couple of the other questions.
Go ahead.
Yeah, so one of them was, Bill, and this may also be for you. The question is, if you don't have finned tube, is it okay to put straight tube back in when you take these samples?
Yeah. Yeah. I talked to Bill about it, so he can answer it. In fact, Doug and I talked about it as well, whether you can put a short section of non-fin tube in, and we thought that it didn't make any difference. But Bill has the experience, if he's still there.
Yeah, typically that's what we'll find is that people won't have fin tubes, so they'll just have an unfinned tube that we'll end up doing the replacement with. I mean, obviously you'll have some gas bypass, but it's somewhat insignificant at that point.
Yeah. Okay, thanks. We've got a question from the
chime-
film of, excuse me?
Bob, if I could just chime in
Sure.
real quick, just piggyback question real quick. So if you go back with a non-fin tube, the next time you take a chemical cleaning sample, are people typically pulling another fin tube, or are they just using that as their chemical cleaning sample moving forward?
From our standpoint, we actually haven't seen a lot of people taking to kind of echo what Barry says. We don't see a lot of people taking tube samples, so I can tell you we haven't run into the situation where we're taking multiple samples in the same boiler.
Okay, thank you.
Yeah, I wouldn't think you would want to take the same tube out twice because it's not going to be representative of
Well, you
what's in the evaporator.
You could, Bob, if you just added, took the one Just added the different deposit
Oh.
weights from each sample.
I see. Just get the incremental deposit from the
Right.
previous point in time. Yeah.
And it's
Um,
quite standard in fossil plants, Bob, to do that.
Is, okay, well, good. Yefim has a good question. He says, what is the spread in deposit thickness between various locations where you might take the sample? Sort of, what are the chances of getting a representative sample?
I don't think that we can answer that.
Yeah,
Uh,
there haven't been enough samples taken, Yefim, to be
Yeah.
able to quantify that.
Yeah, Bob, I think we could just say a little bit more about the sampling, because we talked about it before. We know quite well that that if we take the samples in the areas that I delineated near to the sidewalls and near to the modular gaps, these are the same areas. These are the same areas that experience under deposit corrosion, indicating that you've made the right choice. As compared to in some plants, we've actually taken them in the middle between the modular gap and the sidewall, and they're usually much lower. Okay, and also if you take them from a different location, like at the bottom of the of a tube near the inlet header, or in the middle of a bundle on a horizontal tube surface, you can see. So generally, I think that we've taken enough samples. I indicated how many we've taken and or been asked to look at, and generally, I think the results would agree pretty much with what we put with what I showed you, which is in the IAPS document.
Doug, there's another question for you, going back to the question about how you tell when your cleaning is finished. Can you assume that the cleaning is complete when the iron concentration remains constant? I think you said that works if it's a routine cleaning, but if you're chasing hydrogen damage, it's not necessarily going to tell you that.
Yeah, that's correct. I mean, I always, I know I repeat myself a lot, but you go to an enormous amount of time, expense. You know, chemical cleans are very expensive to do. Why not spend, you know, after your iron levels off in that, why not just let it circulate for 3, 4, 5 more hours? I mean, for the cost and the effort, and I know there's lots of pressure on the other end to get the stupid thing done and all that, but I always pushed back and always told leadership, hey, this is what you spent on this clean. You really don't want to give me another 5 hours of circulation. I mean, when you really take a step back and think about it, it just doesn't make sense to cut it short. How much, you know, I guess the question is, well, how much is enough, Doug? Should I go 1 more hour, 2 more hours, 5 more hours, 10 more? I can't tell you. That's really kind of your judgment. I typically, you know, try to use a rough rule of thumb when I would do a static test that I would typically double it. If that static test said it was 6 hours, I'd clean for 12. That was just something that Doug Hubbard did, but that's an opinion.
Yeah.
But anytime you can extend the amount of time you're circulating, you're got a better chance of being successful.
Yeah, and as you said before, as long as your inhibitor is working, there's no big danger to the boiler in going longer.
That's correct.
Right.
Yeah.
There's a question here that Barry, I think it's for you, but Doug, you may have a thought on this as well. Is like, what's your opinion of a particle counter device? I guess in lieu of taking tube samples to gauge deposit buildup.
Yeah. Yes. I saw that question, and I was going to respond to the gentleman, and we've talked about it at previous meetings. IAPS has a major international project right now to use these proxy methods. It's to be a proxy method for the corrosion product transport, and we've developed the algorithms to use that, and we've also developed a map to indicate to use that process to indicate whether the operation and the shutdown procedures are adequate enough to minimize the amount of corrosion product transport. And there is a white paper from IAPS, which I provided before, and Scott has that information, and I was going to provide this white paper to the person that asked the question, Bob. But basically, you can use it as a proxy method with certain constraints.
Okay, thanks. There's
Bob?
another question. Yes,
Bob,
go ahead, Doug.
I'd like to piggyback on that for a minute. Just, hear Dr. Dooley's message, all right? And I guess that's the most important thing I can say. You should not pull a HP evaporator tube sample and be surprised. And sometimes we're thinking, oh, what's my deposit weight? Well, what's your chemistry been like? Have you met IHOP's requirements for iron transport? If you haven't, your boiler's dirty or your evaporator's dirty. Have you ran with long periods of time with condenser leaks? If you have, you need to clean your unit regardless of what the deposit weights are. Dr. Dooley lays out what you need to do to optimize. If you optimize your chemistry, you're going to optimize when you need to chemical clean, but you can't do both. You can't ignore your chemistry and then say, I'm just going to look at a tube sample and make my decisions. It doesn't work that way. The two go hand in hand.
Yeah. Barry, I see one final question here that says, would cycling have an impact on the length of time between samples?
Yeah, yes. Obviously it would, and it relates to the last question that I just answered about using proxy methods to look at corrosion products during cycling and fast start situations, because we know that those situations are absolutely the worst. And so during a startup, instead of having a normal level of 2 to 5 ppb of corrosion products, you could have hundreds of ppb, and that's what the emphasis of this new activity is, to be able to identify that for your particular unit, so you minimize the corrosion product transport by doing the right stuff during operation and during shutdown, and providing those in the optimum way. But yeah, definitely, if something is cycling every day or multiple times per day, then the corrosion product transport is likely to be much higher, and therefore the buildup of deposits in the HP evaporator are likely to be higher as well.
Okay, thank you. Scott has added links for these guidelines, technical guidelines Barry just mentioned in the chat, if you care to copy those.
Okay.
All right, we've arrived at the end of our 2 hours, and we have answered most, if not all, of the questions. So let me thank both of you, Doug and Barry, for
Yeah, thank you.
it's a very useful presentation.